and in vacuum, which is diverted. Okay, Gauss theorem of electric field, which is completely equivalent to Coulomb's force. Coulomb's force, where a field produced by a charge at the origin is given by E R equal to 4 pi epsilon naught R square. Okay, Q R. Okay, well, R is equal to is a unit vector around direction, so that's X, Y, Z, right? Okay. Now we can okay. This can be derived as a divergent, as a gradient phi, where phi is the electric potential is equal to Q the electric potential produced by a charge Q at the origin is given by this one. Okay, we can calculate that gradient is equal to partial x, partial y, partial z, 1 over r, right? So r is equal to square root x squared plus y squared plus z squared. So partial r, partial x equal to r 1 x over r, right? So the derivative of that, first of all, it's a derivative with respect to r is minus r squared, and then the derivative of r with respect to x, that is x, right? Similar, you have y, you have z, so that we have that one equal to minus r squared 1 over x, y, z, right? That's equal to minus r to the r, right? Okay, that is exactly. So here, that is exactly equal to that one. Okay. So the Coulomb's law at the origin. The Coulomb's law implies that the electric field is a gradient. And for continuous charge distribution, we have phi r minus r prime rho r prime, the integration of this thing. Okay, and the electric field is a gradient of that one. Okay, so this is the implication of Coulomb's law. Now, one implication, okay, suppose, let's take it, there are several implications, okay. So, remember, what is the definition of gradient? The definition of gradient df is equal to f r plus dr minus fr. The value of the function at r and r plus dr plus df is equal to gradient dot dr. Okay, that's one. partial differential equation. Partial f, partial x, dx plus partial f, partial y, dy plus partial f, partial z, dz. Okay. Plus an additional terms which tends to 0 as this displacement dr tends to 0. Okay? So, this is very important. Phi is the electric potential. Phi is the electric potential. Very important. Phi r, electric potential. Okay. So, if we make the integration from position 1 to position 2 of the line integral. Also, this is 1, 2, and we make it a line integration from position 1 to position 2. That means 1 to d minus, because that is greater than phi of dr. Right? And then this is d phi. So that is equal to phi 2 minus phi 1. So the integration, the line integration of phi of the electric potential give you the line integration of the electric field give you the difference. The result is the difference of the electric field. So in this respect, suppose we make around a cos curve. This implies d dot dr is the same distance, the difference of the same position. Okay? So that is 0. Okay? This is an implication of Coulomb field. This is valid for static electric field, for static electric field. Okay, and the point is, okay, force is equal to E, right? This implies that, if you, for example, in a synchrotron light source, okay, light source here nearby, where the electron is confined into a storage ring, run and run, and you want to accelerate. If you want to make an acceleration by an static electric field, it is possible, because the total force F of dr is the work done on the particle. This means that you cannot make a static accelerated electron in a closed orbit by a static electric field. You have to use a time-dependent radio frequency, RF source. Okay. RF radio frequency, whatever. Light of the electric dynamics. Okay, is the microwave in the mirror, which is very useful. A lot of people, earn their money in microwave. Which is very important. All you need is only read mass equation. Okay. We don't have enough time to touch on that. We might touch some of the
some of the. We're going to touch some of them, but we don't have no time. Okay. So it's a complete. It's a complete. It's a very useful field. Okay, but I just want. There's a lot of applications. Communications, power source, and even Wi-Fi. Okay. And even, okay, not just chips. Use some knowledge of this. I think it's RF. Okay, anyway. Version RF. Yeah, lots of. Okay. You know, during the Second World War, okay, they put a lot of physicists in the United States, a lot of physicists in developing, okay, atomic bomb, in addition, atomic everything, and then the microwave engineering just come from there later, okay. Okay, and anyway, so the point is, this is 0 for static field, okay? Okay, and this is related to the fact that, okay, the fact that E can be written as a gradient field, okay? A direct calculation means that curl E. Okay, curl, what is curl E? Partial X, partial Y, partial Z, cos EX, EY, EZ, okay? That's curl, so-called curl of curl E, okay? Or sometimes during, okay, we might see some location that rod E, okay, the same thing, okay. It's curl. Okay, now, so this is that one gradient phi, right? Cross terms, you know. Okay, and write it minus, right? Minus cos phi, okay, the same phi. Okay, so you go. Okay, so all you get the same factors, differentiation, partial x, partial y. The order of differentiation can be exchanged. So this is 0. Okay. So curl E. So E equal to minus gradient phi implied. Okay. In reality, you can prove that. Okay. In fact, you can prove it also the other way. With, I think I gave a proof in the note, right? Curl E equal to 0. Okay. So the field is called laminar field. Okay, you know what is laminar field? Okay, you know in the flow, okay, if you curl V equal to 0, your flow is laminar. Just like layer, laminar field. Okay, sometimes you have a turbulence, then not 0. That's so that kind of thing is not a laminar field. So the laminar field, you don't have this turbulence. You just layer, okay? Okay. So this is the first thing we look, okay? And okay, before we do that, you know, and the second thing is that, okay.
field is minus 3 to 5. Right? So divergent E equal to minus divergent. Okay, and that means you write it partial x, partial y, partial z. Dot partial x, partial y, partial z, right? 5. That is minus Laplace 5. Okay, Laplace. This Laplace operation is very important. This is Laplace operation. Laplace. Laplace is a great French mathematician. Laplace. Okay. So it's pronounced Laplace. I don't know French, but I know how to pronounce this word. Okay, Laplace. It's not Laplace. Okay, it's Laplace. It's a French. It's a French. Okay. Laplace operator. Okay, so it's a this equal to 2. The scalar product of 2 operated by itself. Okay. So if you calculate that, okay, we know that divergent E is equal to what? Epsilon naught, rho over epsilon naught, right? So rho over epsilon naught. This means that the electric field potential, okay? The electric field potential satisfy the, okay, when the right hand side is 0, it's Laplace. When the right hand side is not 0, it's Poisson equation. Poisson equation, okay. Again, it's French. As I told you, I don't know French, but I know how to pronounce it. Poisson, it's not Poisson. It's Poisson. Okay? Poisson equation. Okay? So the electric field satisfies the Poisson equation. Okay? Can we derive that in the other way? Yes. Okay. The point is from 5 equal to 1 over 4 pi epsilon naught. Rho, our problem, the integration of charge. Okay. So, by the way, this is very important. You know, the R, it goes like this as asymptotic. The effect of the charge from the line range is 1 over R. The Coulomb field is a long range field. That makes calculation very difficult. You know, in quantum mechanics, you have molecules, you have a lot of electrons, right? You have a quantum mechanics very calculation. But most difficult part is the accurate calculation of this classical effect. This one may, in the molecule, okay, there are a lot of complicated quantum mechanics theoretical. All those parts, okay, theoretically it's very difficult, but to have a calculation, this is the one. This is the trouble which make just a very accurate calculation of helium atom. It's very difficult, right? The second dimension. Okay. Anyway, that's another story. Okay. Now, let's calculate this one. Laplace 5. Okay? 5, we are differentiation with respect to r, not r prime. Okay? So this one is okay, rho r prime. The Laplace does not work on that. Okay. So we need to calculate this one. Okay. Just for simplicity, let's first make the r prime equal to 0. Okay. Laplace r prime, but just for simplicity, here the same thing. Okay. This one is very simple. One over r. Okay. Minus r squared, and then r over x, right? Notice that, right? So it's minus r3x. So 1 over r equal to, first you differentiation with respect to x. R3, 1, right? And then differentiate with the r. So that's 3 r to the 4 r to the x. Okay. We met this before. Right? Minus 1 over r3 plus 3 r to the 5th x squared. So again, okay, when r is not 0, we have Laplace 1 over r equal to 3 plus 3 1 over x squared plus y squared plus z squared over r to the 5th. Right? So that's 0. Okay, so in general, we know that minus r prime is 0 for r not equal to r prime. Okay? And so when we make this integration, everything is 0. Everything is 0. R not equal to r prime. Everything is 0. Okay, and so in general, when r is not equal to r prime, everything is 0. Only the value of around r. Okay. Okay, the value around r then is divergent. Okay. Then so. How do we calculate that? Make it sphere. Okay. Make it rho r. Okay, because we can make this sphere as small as possible. Okay. However, everything is 0. Okay. So only r prime, this sphere can be as small as possible. So the value of that one, okay, it's around this one here. Its value, and then this is very small because that is continuous. So we can take that out. We can take that out, right? So this integration can be written as, okay, take that out. It doesn't matter. Okay. Laplace. Okay. Laplace is divergent to Laplace. Okay. Now let R equal to 0. So it's divergent gradient. Right? So we make a divergent with the integration of divergent gradient right? Divergent something is equal to the surface around. Okay. Alpha, right? Partial n. The gradient of that, the gradient of r equal to r3 to the r, right? And a sign. Check. Minus sign. Or I can take that one r square, right? So this is r square r minus 1, and then n dot that one square a, right? So n is that is the same for r squared, cancel out. So what do you get? Minus sign here. So make that one, it's a minus sign there, 4 pi, cancel this one, equal to epsilon rho. So this okay, this one is 0 for r equal to r not 0, right? And the same anything integration is equal to minus 4 pi of that value at the origin here. Okay. Whatever. Okay. At the origin. This is called three-dimensional Dirac delta function. The Dirac function is the one where fx is equal to 0 for x not 0, but fx dx is 1. That's called Dirac function. Okay? Delta function. Okay. That's one dimension. Here we have a three dimension. So we have this one. Just memorize this. 4 pi delta r. Okay? It is three-dimensional delta function, Dirac delta function. Or you can check the origin. R minus r prime is equal to minus 4 pi delta r minus r prime. Okay, the effect of delta function is when you make a three-dimensional integration, all the functions just get the value at the r prime. Okay, and then 4 pi. This is the delta function. So this is very useful. I want you to memorize this and know how to use it. Okay, and then you can forget about it. All these complicated things.
老师，我刚刚有点卡住，那为什么可以打出来？
No.
对，那个地方。
Okay. For those values, r prime is something r. Okay, it's 0. You don't need it, right? Okay. You only want to get the value near r, right? Because the rho is continuous. Its value is as near as possible. Okay. When the space is very small, it is equal to rho r. Okay.
So, so all these complicated things, okay, we can do. Okay, calculate this, forget about all this one, just remember this delta function. When you memorize it, when you use delta function, just remember this one minus 4 pi delta r minus r prime. Okay, so Laplace phi equal to 1 over 4 pi epsilon naught. Okay, no, I don't care. Laplace 1 over r minus r prime. Okay, now you can then insert this 4 pi epsilon naught rho r prime minus 4 pi delta r minus r prime. Okay, and the integration. And this is 0 when r prime is not equal to r. So this 0, and when r prime equal to r, that's rho r. And the integration is 1. So that is 4 pi epsilon naught rho r minus 4 pi. That's it. Okay, what's the equation? Okay. This is the bed. Okay. So I want you, okay, to forget about everything. Forget about everything. Just memorize how to use this one. Okay? Then you are a so-called, very high class, very, how do you call it? Expert. Okay, then you are expert. Okay. You don't need to memorize all these complicated things. Sometimes it's confusing. Okay? Just remember this one. Just remember this one. Then you become expert. Okay. That's all. Just remember that formula. Okay? Remember, this is three-dimensional. Okay. Delta R is not equal to delta R. Okay? It's okay, suppose it's spherical. Okay. Delta R equal to 1. So that is not right. Okay, and when you make an integration, that is delta R 4 pi r squared. PR, something like that. So, there is a proportion. Was very constant. One dimensional delta R, no. Okay, and then if you want to make it one dimension, it's not equal to that one. Okay? Just be careful for this 3 dimension and 1 dimension. There's a proportionality. Okay. We'll talk about that later. Okay. So that's we can stop it for now. Okay. Now. Okay. We have a Poisson equation. We have Laplace equation. We'll come back later. We will come back later to Poisson equation and Laplace equation. Okay? Now, that's Gauss. Okay? The Gauss law of electric field. Now, how about? Okay. I think this. Okay, so how about amperes? Second law. Okay,
Ampere second law is suppose you have a current through I there, and then you make it round. B dot dr equal to mu 0 I, the total current. Okay, suppose you have a loop. You have a loop. Okay, and you make it around B dot dr. Okay, that equal to the total current going through that inside a loop, right? So you make a surface, okay? That is equal to mu 0 R is what? R is J dot N, right? J is, this is the current passing through the surface per unit time per unit area. J dot J, okay? So this is Ampere's second law. And then Ampere's about the surface, okay? And then we can use the so-called Stokes theorem. Stokes theorem states that a circular line integral of B around the circular is equal to the curve B, the normal component of curve B, the surface area, okay, of the surface. So this is surface, circular. That's surface, okay? So any surface, you have that one, they are equal. So that means the differential equation is that curve B equal to mu 0 J, okay? So that's Ampere's second law, okay? By taking divergence, this implies divergence J equal to 0. And that means, so we have a divergence J plus partial rho partial T equal to 0. That means it is a static case. The current is conserved. Okay. From a picture point of view, your current goes through that. Suppose you make a surface here, okay? These are the same. Total current coming out are the same. Coming out are the same, okay? Coming out from this space or this surface are the same. So you turn it around, whatever coming in is coming out. So that means J dot N. Okay, you make it surface. This one coming in. This equal to this minus this is this plus this one by reversing the normal component. So this is 0. And that's divergence J equal to 0. Okay. Okay, the same thing. Okay. Sorry, this is the same thing. So that's Ampere's law. So we'll come back later. Okay. The more interesting, more involved is okay. I will choose this. Faraday's law of induction. Okay. Oh, we just learned that for static field, E is equal to minus gradient phi, right? With phi potential. So, in particular, a closed curve, okay, that is 0 for static field. Now, so you know that F equal to QE. Okay, and so F dot dr QE dot dr. So QE dot dr, this one is some kind of word. Okay. Now, for time changing, when the flux, this magnetic flux is changing, it turns out this is not zero. This is so-called EMF, electromotive force. Electromotive force. Okay, the reason you have this one, electromotive force, is because during those times everything has to have a mechanical equivalence. So you must have some kind of electromotive force or something like that. Actually, as a student, I don't understand how it comes from. Now I know that it's just wrong. Okay, it is historically there's no no real so-called electromotive force. It is just disintegration. Okay. Okay. Don't connect with that with any mechanical things. Not no reason, but it's a historical reason. Because electromotive force is equal to a circular integration of that. It is found out that when the magnetic flux is changing, okay, it produces equal to the total magnetic flux coming through the surface encircled by this curve. Okay, this is Faraday's law of induction. Very, very significant. Very, very significant. It is. So what is magnetic flux? Very simple. That is okay. So just as Gauss law, we call that electric flux density, because when there's a vacuum, okay, when there's a vacuum, okay, when vacuum divergent E is zero, the electric flux coming in and coming out, E dot N is zero. So you think that there's some kind of electric flux going in and going out, electric flux. And for the same thing, this is called the magnetic flux. B is magnetic flux density. So this is the total magnetic flux. Okay. Okay. Well, this is very important. In Ampere, they don't have vector calculus. They just draw this line, Very ingenious. Okay, whatever. Okay. We now know that. Okay. This is historically magnetic flux. Okay, flux density. B is magnetic flux density, and the change. So the change of the total magnetic flux passing through this surface is equal to this so-called electromotive force. Okay? Okay. Yeah, very, very many significant. This is the first time the electric field and the magnetic field, they are really the same thing. Okay, or related. Okay? That's the first thing. And another thing, we call this magnetic flux, right? Okay, you have the surface, this surface. Suppose, no, I want to take the surface here. Okay, and the circle here, right? So, they must be the same. For S1, S2 must be the same, right? So,
an implication of an implicit implication of Faraday's law of induction already means that for a closed surface, you change this out. This surface the same. Okay, you change this out. For a closed surface, this is 0, right? For a closed surface. Something in, something out. And this implies divergent B. So Gauss, magnetic version of Gauss divergence theorem, is already implicit. Okay, you cannot say implicit. This must be the same. Otherwise, this would be very difficult. Which magnetic flux are you going to use, right? So they must be the same. So the magnetic flux is conserved, right? So divergent B is 0, right? Right? Divergent B is 0. Okay, so. Okay, now. Okay, we have a E equal to curl minus radian phi implies divergent curl E equals 0, okay? Okay, this is now the same thing. B, okay, divergent B equal to 0 imply, actually that's the same. B is equal to curl A. The magnetic field has to be a curl of a vector potential. Okay, so that is for time changing, you have to modify this one. Okay, but this one always holds. Okay, this one always holds. Magnetic field. Okay, so Faraday's law of induction. Okay, I imply implicit this method. Okay. If they are different, then you have to explain. So it's more natural. It's more natural, right? It's the best thing to assume is that they are actually the same. The magnetic field does not depend on which surface. It's all the same. This is implicitly right here. Okay, Faraday's law of induction. So you have the Coulomb force, Gauss law, Ampere's law, Faraday's law of induction, and Gauss law, magnetic version of Gauss law. Okay. Now all you have to do is that this one is not inconsistent, and that's a contribution of Maxwell. Maxwell just add a Maxwell displacement current, JD. Okay. Which JD he found out is equal to epsilon naught partial E partial T or partial D partial T. And make everything just compact. That's all. Okay. I already posted a homework in the MS. Okay. Due next Tuesday. Okay. And because one of the TA is a international student, so you have to hand in English. Okay, don't worry. Try to do that. Okay, try to do it. Okay. Don't worry. Don't worry. You have to try. Okay, why India? Okay, Singapore and Hong Kong. Okay, why they become a world center, a lot of work activities. Because of what? Because of English. So if you want to be successful, you better try to use English. Okay? It's simple. You look at all those American football players. They are stupid, but their English is very good, right? Good. Okay, that's a joke. What? Okay. Okay, we got to go. Okay.
Bye bye.